the cloud. Okay. Now we're recording and chat. Okay, can you guys see the Karush-Kuhn-Tucker condition slide there online?
Yeah.
Okay, I'm gonna, if I advance it, does it? Okay, did it just advance the slide?
Yeah.
Yes, okay, good, let's go back. Okay, so we were talking about numerical optimization. We were talking about the mathematical conditions to help you, like I say, expedite your search within an unknown function and sort of space and what it looks like. And we talked about the necessary conditions for, you know, if you weren't at a local or global maximum or minimum, how would you know? Certain conditions that you would have to meet, and that's kind of a theoretical basis that your computer might use to determine if you hit that local minimum or maximum. So suppose you had a another function, another f of x, we'll call it, and here we have a design space x1 and x2, and let's just suppose for a second that the design space kind of looked like this. You had you know, some contours, okay, right? Okay, we'll call this let's see here, we'll call this f of x1, x2. Guys, I'm sorry you can't see this on, I don't know how well you can see this on the screen. I'm doing the best I can here. But, okay, equals to D1. You had f of x1, x2 equals to D2. And you had f of x1, x2 equals to D3. And you kind of know beforehand already that the let's just say for our sake of this discussion right now, we know that D1 is less than D2 is less than D3. Okay? And the problem is, okay, fine. So A, the minimum of x is a function of x1 and x2, subject to your constraint g of x1, x2 equals to 0. Okay, yes?
For the x1, x2, and x2, are they multiplied together, or is it like x1 comma x2?
Yeah, I'm sorry. It's supposed to be x1 comma x2, and then I just extended the x is what I did. So there's actually supposed to be a comma, okay? So it's f of x is a function of x1 and x2. And so is g of x. Okay, so at first this looks a little strange to me that this equals to 0. You know, but when I went back and I thought about some of the examples I showed you a couple of weeks ago, where we had those, where we had a column that was under buckling, and we had the 3 trusses, and we always sort of, and you had the constraints were always about stress, like don't get the stress above a certain point or else this thing's going to break. And the way that we sort of structured that requirement into a constraint was that we made it that the stress that the actual part has on it minus the critical stress equals to 0. So you can, and then you can easily plug in for sigma, you know, stress and stress critical, you know, based on the geometry of the beam or the bar or whatever it was. Okay, you guys remember that? And then you can set that equal to 0. Okay, so that's why this kind of does make sense. So let's say that we know, and I wish I had colored chalk here, but I don't. Let's say that we know that the function g of x kind of goes crazy like this. Okay, so this is g of x1, x2 equals to 0. Okay, now there's this function called the gradient. I think you probably learned it in calculus at one point, right? I don't remember what year it was, maybe in second semester calculus. And the gradient points towards the optima of the function, the minimum or the maximum. And it's perpendicular to the curve at a given point. So at a given point, it's always going to be perpendicular to the tangent of that curve, and it's going to point to the optimum. So we can start thinking in terms of this little bubble here, like this little mountaintop kind of thing. At this point here, the gradient points down. At this point here, the gradient points that way. At this point here, the gradient points that way. At this point here, the gradient points that way. Okay, and we can do that all around here. We can put these little gradients everywhere on our function f of x that point towards, that are perpendicular to the tangent of the curve at that point, and they point towards the optimum of the function if you're looking from that point. Right? We put these all over the place. Make sense? So, yes,
So
Sophia.
it's perpendicular, yeah, like up the steepness, I guess you could say, but it's not necessarily perpendicular to like that line, right?
Which line?
Like the outer, like I'm looking at the arrows of the outer, like that one right there.
So this, you can think of this as just your calculus, right? This is a point here. You can draw a tangent to that point, which is the derivative, right? Okay, and then the gradient points perpendicular to that tangent.
Oh, and then it's depending, okay, I got it.
Okay, so we have this design space, x1 and x2. And you can kind of mentally walk around this design space, and you can calculate a whole field, a whole bunch of gradients over this design space. Right? There's a whole vector field. A gradient can be a vector. The whole vector field, and they all point perpendicular to the tangent of the curve at that point. And like I said, you can think of this as the whole field of vectors pointing in some direction that's an optimum. Right? Now you can also, as it turns out, do the same thing with the constraint G. You can start thinking in terms of tangents and gradients for the function G as well. Okay, at this point right here. Okay. So, subject to this constraint G, you can think about how this might look. So, at this point, for example, right here, where it crosses over this D3 line, f of x equals D3. At that point right there, you can think that the gradient of the constraint faces like that direction. I'm exaggerating the size here just so you can see it. Okay, at the same point, okay, for f of x, the gradient points that way. Those two are not parallel. You see that? Actually, wrong direction. It goes, my mistake, sorry. It goes this way. So here's the gradient of f of x at that point. Here's the gradient of g of x, and x is equal to x1 comma x2 at that point. They're not parallel. You guys see that? As you start, and if you think about it, f of x on this line, this contour line equals d3. We know d3 is more than d2 is more than d1. So we know we haven't hit that minimum. Make sense? Got it? Okay. And then let's say we kind of travel a little bit further along this line where g of x equals to 0. Get to this point right here. The gradient at that point for the constraint is going this direction, and the gradient of the f of x is going that direction. Are they parallel? No. And so on. You could think of, these contours are chosen at random. You could draw infinite number of contours within this design space for f of x equals to some constant or some constant plus a fraction, whatever. Right? There's infinite number of these things. But as you get towards this one right here, f of x equals to d of 1. Here, if you pick that point where the two are intersecting, that contour and the constraint, at this point, the gradient of g of x is pointing this way, and the gradient of f of x is pointed this way. And so that means that their tangents are parallel. This is the point where you know you've hit an optimum, in this case, a minimum. Okay, and again, I'm only telling you this so that you understand, like, there's a computer program out there somewhere that's trying to figure out, okay, I've worked through this function, I've gone this direction, I've taken this step, I've done all these things, I've come to some point, I'm calculating a new value for f of x. Am I good, or I have to keep going? This is the point where you say, I'm good. This is the minimum right here. You hit that contour line subject to this constraint here. If we go past this point, we go up here somewhere. Let's say we go to here. The gradient of g of x is this way, and the gradient of d of f of x is now it's like this one. See that? So this is, we know we've left our optimum, our minimum at that point. That's when you know you've gone back. So this is the necessary condition for the optimum. But the condition for the optimum is really the gradient of f x1 comma x2 equals to the gradient of g of x1 and x2. Okay, you see that? Okay, this is where those two vectors are, those two gradient vectors are parallel. But the problem is that this one's a boatload longer than this one. You see that when I've drawn it up there? Which means you have to multiply times some constant so that they truly do cancel each other out. That the vector math works out so the two will cancel each other out. And that's this lambda. This is called a Lagrangian multiplier. You guys remember that from calculus? When I took calculus, I saw this, but I sort of said, okay, that's interesting. I learned what I had to do to pass the test, you know, got the A, and that was the end of it. But I never, it took many years later when I started thinking about optimization, when I was at Chrysler working on lightweighting bodies, lightweighting car parts, that all of a sudden this Lagrangian multiplier became interesting to me. So I'm showing you now, like, this is why this is interesting. This is where you end up using this. So if you guys remember, we talked about last lecture, we talked about that we have an unconstrained optimization problem, right? That you can find the optimum of that function by taking the derivative and setting it equal to 0, right? That's first year calculus. Okay, when you have a constrained problem, like we showed, that doesn't work anymore. And this is where the mathematicians invented the Lagrangian principle or method or multiplier, whatever you want to call it. And what it says basically is that you have some Lagrangian, they call it L equals to f of x1 comma x2 minus the Lagrangian multiplier times g of x1 and x2. Okay, this is sort of a, I'm not sure if this is an intuitive equation or not. This is something that they call an auxiliary equation that the mathematicians came up with. It turns out that if you take the gradient of L, which is called the Lagrangian, and it's a function of x1, x2, and this Lagrangian multiplier lambda. If this, in the condition when this equals to 0, this is your optimum. Okay? The thing that's cool about this is with the unconstrained problem, we said that you can just take the first derivative and set it equal to 0. That's where your optima are. And then with the constrained problem, you can't do that. This allows you to do that with the constrained problem. So now you can just take the first derivative of this Lagrangian multiplier, which is effectively taking the gradient. Okay, and you can set, and we know when it equals to 0, you hit your optimum. So you guys copy this down? I think I got the order wrong here before. Sorry. So now you can think in terms of the Lagrangian, the gradient of the Lagrangian equals to the set of these derivatives. So the partial derivative of L with respect to x1, the partial derivative of the Lagrangian with respect to x2, and the partial derivative of the Lagrangian per lambda. Okay. So this is kind of abstract, and there's, if you go on Wikipedia, for example, you'll see this exact same example. I lifted off there because I thought it was a good one. But you can read about this in more detail, but if you're interested. But it's interesting to me that you know, this can be something that you can calculate. This comes out to some number. This comes out to some number. I'm sorry, this comes out to 0. This comes out to 0, and then this comes out to. If you take the derivative of this equation with respect to lambda, and you have to get necessarily, because this has to equal 0, you get this equal to 0. So g of x equals g of x1 x2 equals 0, which is our condition up there. Okay, that's where I'm going to stop with this part about all these crazy derivatives and stuff and vector math and all those sorts of things. Okay, it's weird, it's abstract, it's kind of got all these crazy math symbols. It's interesting at this point for me to kind of learn more about this. It was back, a couple years ago. If you want to read more about this, there's all kinds of stuff online. I've watched a bunch of YouTube videos of people explaining this and so forth. So it's the theoretical basis for optimization. Jeff, any questions? Okay, good. I'm going to move on. Finite element analysis. Lucas, you there? Tyler?
Yeah.
So, let's see if I can make this bigger for you guys. The last, not the last round of student presentations, but the one before that, Tyler gave a presentation on finite element analysis, and I think he described one facet of it, which was kind of an advanced portion of finite element analysis, understanding what is good and what is bad. I'm going to kind of go a little bit further back and talk about the basics, okay? And anyway, so we start here. Okay, so if you have a simple column beam that's in tension or compression, shear, or whatever, it's very easy to calculate out the stress that's in the cross section. Just force divided by area, right? You probably learned that, whatever your first, mechanics class, or you learned it with you guys, Beer and Johnson, was it? Great book, one of my favorites. It's pretty simple stuff, okay? In the real world, when you're designing real parts that end up in real airplanes or cars or boats or buildings or bridges or whatever, it's rarely that simple. The geometry of the part is far more complex. The loading conditions are far more complex. And you can't just do force divided by area, because what area you're going to use, what's the direction of the force, it becomes much more complicated. So that's why we invented this thing called finite element analysis. Finite element analysis is a way of calculating, you guys probably know this already, it's a way of calculating the stress when you have far more complicated geometries and boundary conditions, also known as loading conditions. All right, so right here I have a picture of a connecting rod. The connecting rod might be in a car engine, might be in a boat engine, might be in a tractor. And this connecting rod is subject to some stress. It's there's some pin up here that's pushing down, reacting on a pin down here that's pushing down the crankshaft. And then you've got this complex loading condition. So this is because of like these point loads and the fact that it's not always completely two opposing forces. Sometimes there's a moment on there. It's far more complex to understand what the stress is on this part, and therefore it's more difficult to choose a material. It's more difficult to do choose a material, a cross section, a fatigue limit. It all becomes much more complicated. So that's why we have finite element analysis. And what you do, you guys probably know this already, is you break up the structure into a bunch of smaller little pieces. They call this discretization. All right. And these little pieces can be thought of as some nodes connected by some springs. And the springs, the spring constants, or the K of those springs, Hooke's law, is somehow related to the material properties. All right. Here's a really simple example. This is like a 1D finite element analysis problem. a spring with two different forces acting on it. The spring has spring constant K. So general Hooke's law applies here. You know, the force equals the spring, this K, the stiffness constant times the displacement X. It's very easy to draw a free body diagram and come up with three equations. P plus P1 plus P2 equals 0 because it's not accelerating off into the distance. Then you can take you can draw these two, you can write these two equations here, which are, turn this. Draw these two equations, you take these, you can write these two equations here, which are just X, so just Hooke's law for this particular set of geometries. It's easy to think of this in terms of these equations in terms of a matrix, right? You take these equations, you put them in the matrix, pretty simple stuff. And then you basically solve this for X, the matrix X, which is the displacements. Okay, you know the displacements, you can divide it by the length of the spring L, come up with a strain. Once you have a strain, you can multiply times the Young modulus if it's isotropic. Young's modulus of the material, and you get a stress, right? That's how you would calculate the stress in a member that was like a structural member that was loaded in this way. Okay, it's all pretty simple, right? You guys seen this before? Sophia, you've seen it? How about you guys? A little bit? A little bit? Okay. Now here's the thing. This gets far crazy more complicated, like exponentially more complicated, once you start talking about more complex conditions, more than loading in one direction. When you go from a 1D problem to a 2D problem to a 3D problem, these things just blow up and the equations go crazy. I'm going to try to explain some of this to you about how finite element analysis works when you get past the 1D problem. I'm going to show you a 2D finite element analysis. All right. And the reason I want to show it to you is not to prove you how bad I am at math, but rather to show you that this stuff is very complicated. And also, there are approximations involved. There are huge approximations involved in finite element analysis. So if the day comes that you're standing in front of somebody and they say, well, the finite element analysis shows that this is the answer. And that's gospel. Like the stress on this thing is 350 megapascals, period, because that's what the finite element analysis shows. You can laugh because it's plus or minus some tolerance, like everything else in life. Right? So just keep that in mind. That's why I'm showing you this. The math, even for the 2D problem, gets pretty ugly. All right. And I'm sure there was once a time, I don't know, 50, 60 years ago, 70 years ago, where there was probably a group of people who were the anti-FEA people and pro-FEA people. And these people probably argued with each other about whether this was really feasible to do these stress analyses on complex structures given complex loading conditions. All right. And they probably argued with each other because the math is ugly. My point being, it took somebody, or took probably thousands of people many years to sort of figure out all these mathematics to the point where it would work and you could program it into an algorithm and throw it in a computer and let the computer solve it. Okay, understand? So I'm going to try. So you have this this element right here. Okay, it's got three nodes. For this element, you can think of a displacement at each of those three nodes, which is equal to this little lowercase u times n, which is like a shape function, times the vector d, which is all those displacements shoved into a vertical matrix. Okay, right? And n is the part here where this is sort of like it's some shape function. We're saying if you pull this thing, it's going to sort of deform literally. We'll call it this n, or it could be parabolic, or it could be logarithmic, or a bunch of other functions. It could be a polynomial. N is sort of the approximation about what they think is going to happen. What the people who wrote finite element analysis think is going to happen. The strain is equal to this displacement matrix D times B, and B is called the strain displacement matrix. And I have yet to quite completely understand what the strain displacement matrix is, but I think it has something to do with the length, because the way you would get from displacement to strain has to involve a length. There's got to be something. There has to be a length factor in that B, in that strain displacement matrix. The stress is equal to this value big D. Okay, where big D is a matrix of stiffness. okay? Times these other two, right? And that's stress. All right? And then you can go ahead and you can calculate out the stiffness matrix for that over the volume of that element. And it's equal to the transpose of B times D times B times this little piece of volume. And you have this BT and this B transpose and this B in here because that makes it a square matrix, which makes it easier to multiply times D, which is the stiffness matrix. Right, okay. So here's your 3-degree element, your triangular element. It has 3 degrees, and it's 3 nodes. Each node has 2 degrees of freedom, X and Y. And that means that there's 6 degrees of freedom per triangular element, right? You can write out the movement of, or this U here, which we said before was this guy right here, which is this is how the elements move. All right. You can write those out as a function of n and x and y. And again, n is this weird shape function. One thing you might see sometimes is called piecewise polynomial interpolation. Some finite element codes will use that, which is just an approximation for where these elements are going to go when the bigger picture structure is strained. And n, you can think of n in terms of these a, b, and c's. So a, b, and c's are some number, some scalar that you multiply these polynomials, which is your approximation for n. And you can solve for each one of those. You can then take the previous equation, plug it into this matrix, or this matrix equation right here. Okay. And then you can calculate the strain by understanding that the strain is equal to the partial derivative of u with respect to x, the partial derivative of v with respect to y, and then the shear component is the addition of those two. Plugging in those equations for n in the previous slide, that one, into these partial derivatives you work through, you can come up with these 3 expressions of what those different strains are, the different epsilons and gamma, as a function of little a, little b, little c, and a, which is the big A, which is the area. And eventually you calculate out this strain displacement matrix B, which has A in it, so there's some functional length in there, or A length. Plug that into K. K is the stiffness matrix. You can add together stiffness matrices for the entire assemblage of these little elements. All right, and then from there, you can calculate out a stress. Okay, this is some pretty crazy math from my perspective. I'm sure there's people in this building who can do a far better job of figuring this out, understanding this math. But the point I'm just trying to get across is that there are huge approximations involved in finite element analysis. It's hugely complex. It was developed over years and years. We take it for granted today. I took it for granted because it was developed by the time I was in college too. But there was probably thousands of people who worked on this. Probably the hard work and result of thousands of people figured this out. And they probably, like I said, there's probably anti-FEA people, pro-FEA people. It'll never work. It'll work great. And they eventually all worked together and came up with this. It's very complicated. It's very ripe to be thrown into an algorithm and thrown into a computer and sort of put in the information and stand back and let it do its job. All right, so that's what I want you to remember. There's extreme complexity here. It gets even worse when you have a 3D element, right? And this is something that's very nice for a computer to solve. And you probably in your careers will never actually have to solve this by hand, but just know that when you use when you pull down your ANSYS program or Abacus or whatever it is, all this stuff is going on in there and it's extremely complex, and just appreciate that and understand that there's approximations involved, and you should always question whether you're getting garbage in, garbage out. Okay? Any questions online about FEA? Okay, so we're going to talk now about load path optimization, which is kind of the place where finite element analysis and numerical optimization meet. Okay, suppose you had 2 opposing forces F, both of equal magnitude, both F, right? And you've got these 2 structures here. You've got this one little bar that's between the 2, and then you've got this crazy thing where it curves around, it goes up and down, it backs around. There's all kinds of moments in there. Assume it's made out of the same material. which, if you could define kind of loosely structural efficiency as say stiffness or strength is a function of weight divided by weight, normalized by weight. Which one of these do you think would have a higher efficiency, higher structural efficiency? The one on the right or the one on the left? The one on the left, exactly. All right. This seems very straightforward, but you'd be surprised that there's actually structures out there that you guys see every day that aren't quite as clean as this. Here is the front end of a Mini Cooper. Okay, I have friends who work on the Mini Cooper, the first generation Mini Cooper, and I think it's a neat little car. I like it a lot. I think that there were certainly some compromises put in there for the sake of styling. All right, and with every car that's true. But you can kind of see here that it's an analogous situation. When you have a car and you have springs that are pushing down the wheels and the suspension, the main forces that go into the chassis go through those springs. So there's also a damper in there too, so you don't get a resonant frequency on the freeway. Those forces feed into the body structure, these things we talked about before called the shock towers, right? So you can kind of imagine the main forces are coming up through these shock towers. Eventually, you have to feed those loads over the roof and back to the rear shock towers, right? And rather than having a very simple, clean load path like we did here, we've got something more that's like on the right, actually. And the loads come up and they bend around here and they go back up these 8 pillars. What would be the most efficient would just be like a bridge where you just have sort of like an arch over the wheels. Does that make sense? So there's inefficiencies associated with this. Okay. This drawing over here shows how there might be a more convenient or more efficient way to do this, where you just have the shock towers going directly to the bottom of the 8 pillars, and then the load goes over the roof of the vehicle, down the C pillars to the rear shock towers. That's much more efficient than what we have in the first one. You guys copy this? So you can kind of think of this in terms of, here's some loads that are coming up through the shock towers. You can have this situation, or you can just have this situation. See the difference? You see how one is sort of the complicated stress flow. Okay, one of them is introducing more moments into the design. Okay, this one is more efficient. This one is a much more direct load path. The direct load path would be the one that weighs less. It's more structurally efficient. And you get higher strength per weight, which is what we're after. That's what this class is about. Okay, so this is the geometrical part of this, right? We talked about materials. We talked about how you use computational materials engineering methods, for example, to develop materials that have a high strength to density or high stiffness to density ratio. Okay, this is now the geometrical part of this. How do you design the geometry of a part so you have the highest chance of a good structural efficiency? So the load path through a given structure, or say the place where a structure can live, and maybe has complicated boundary conditions, is not always that straightforward to figure out, right? When we have the 2 opposing forces, that's pretty easy. You just put a beam in between. But when you have a complicated shape, like a car body, and you have people that are sitting there, you can't put the structure that's the most efficient place always. You've got crazy geometry, all kinds of curves and bends and ups and downs. Then it becomes a little more complicated to intuitively understand where does the structure go. So there's a great paper by Benzo and Kikuchi from 1988. You can go to the library and open this one up. It's a great paper. I've read it a couple times. It's lots of fun. These guys basically discovered or invented a method called topology optimization that allows an engineer to calculate the most efficient load paths through a given packaging volume. Right? This tool called topology optimization has become, I think, ubiquitous in the automotive industry. I'm pretty sure all the major automotive manufacturers were or have been using this tool for about a decade now. Okay, I'll show you later. I have proof that Honda's used it and Audi's used it. But this is This is a very, very useful tool, something you guys should know. So the story goes like this. The paper talks about this. They say, suppose you have some complicated volume. The volume is a place where you can put structure. So that's a little hard to figure out sometimes. Suppose you had a car. You can't put a structural member through the driver's head. They have to have someplace to sit. So you define what they call a domain. These are places where you can have structure. Right? This packaging volume, as we call it, packaging volume, has these loading conditions, these boundary conditions. They're potentially very complex. They've got a load coming in here and a load coming in there, and it's fixed here and it's fixed there. And it can be all these different load conditions, these boundary conditions coming into that volume, which make this even less intuitive. Kikuchi and Benzoa, they discretized this volume, effectively with finite element analysis. And then they designated a density for each of those elements between 0 and 1. And then they equated the density to a stiffness for that element and a mass for that element. Assuming the density starts off at 1, you calculate out the stiffness of this whole thing based on finite element analysis, or the strain energy, or the strength. And then what you do is you start saying, suppose that the density isn't, we don't have a full 1 for every element. We have to be more strategic about where we place our mass in order to get the stiffest, most efficient structure. So this is where the numerical optimization part comes in. You have this design space. It's been discretized. Maybe it's got 500, 1,000, 1 million, 2 million elements, whatever it is. And each one of those elements has a density associated with it. The density is the design variable. So remember I told you guys before that we were dealing with some pretty simple stuff here. We had a 2-dimensional design space, x1 and x2. These guys took that a much step further, and now you have a design space that could be 2,000 densities, it could be 1 million densities, it could be 10 billion densities. And then the question is how do you distribute your mass so that you have the most efficient structure? And the way that they did this is they calculate out what's called the strain energy, which is 1/2 kx, so it's kind of like the area underneath the triangle. It's linear elastic, right? So the area inside the triangle is 1/2 kx. They calculate out the strain density, the strain energy for each one of these elements subject to these boundary conditions. Okay, and then what they do is they add up the aggregate strain energy of this whole system. So if it had 5,000 elements, they'd have 5,000 numbers added together, 5,000 strain energies. The strain energy, remember, is 1/2 kx, okay, where the k is calculated from the density. It's called a homogenization approach. I'm not going to get into that here, but there's a way to go. They've done this function. They've created this homogenization function where they go from density to mass and to stiffness. And then the optimization problem is to choose the density of each element so that the aggregate strain energy is minimized. You add up all these different little pieces of strain energy, which is the strain energy for each of those elements, right? Given some density. And then you're trying to find a place where that n-dimensional hyper design space is minimum. This is where finite element analysis, because you need finite element analysis in order to calculate out the D here, or the strain of each element. And then numerical optimization. If you have n design variables, how do you find the place where those n design variables are the best value so that you get the lowest aggregate strain energy? Here's a simple example. Again, we'll go back to our beam that's under compression. And we discretize this into, say, 3 elements. Our design space has how many dimensions, guys? 3, exactly. You have each axis, each of the 3 axes is density. Row 1, row 2, row 3, that's the density for each of these elements. Using this homogenization approach, you can then calculate out a K and a mass for each of those guys. You can plug those into a aggregate strain energy. So you take the strain energy for each element and add them up, and then your objective function, we've talked about this obviously before, the objective function has to be minimized. This is your objective function. It's the aggregate, it's the sum aggregate of all the strain energies. So you're choosing densities for each of those three elements in this case, so that the aggregate strain energy is minimum. Does that make sense in terms of the kind of the theory I showed you before? Or this is the theory, I guess. Got it? Suppose you had a beam. This beam right here, the beam is in cantilever. Now, I happen to have looked this up in a book and I know what the stress field looks like. So these are contours of stress, constant stress contours for this beam in cantilever, okay, and bending. It's fixed at the left. There's a force on the right equal to F. You can use finite element analysis, right, to calculate out the stress and the strain. You discretize this out into n different elements. You initially assign a density to each of these 500 elements. And then from that, you can use a homogenization approach to calculate out a stiffness matrix for each element and a mass. This is a contour graph of strain energy, color graph, right? And the equation for the aggregate strain energy is given right here. The numerical optimization routine then goes through and finds out if I've got, so much, you start off with so much density, right? Then you're going to say, I'm going to limit that amount of density. I don't have this big amount anymore. I've only got this little bit. And I have to figure out, the numerical optimizer has to figure out, where am I going to put this density? Here, here, here. Where am I going to put this density so that the aggregate strain energy is minimized? And this is actually the result right here. This is for 500 elements. This is, because of computer algorithms, this is very easily expanded to millions of elements or hundreds of thousands of elements. So this is the easy problem I just showed you. This is the more complicated program, or the more complicated version of this in the real world that is used at car companies all the time to figure out what are the most efficient load paths through a body structure.
I have a question for you, Don.
Yeah, what's up, Sam?
That shape looks, relatively organic compared to something that might be like easily stamped or produced, or like spot welded, the way they make car bodies.
Right.
Is it then like reviewed again for producibility to find like a cheapest manufacturing method, or is that something we're going to get into?
We're going to get into that in the next couple slides here. We're almost done for the day, but talk about it for a second. The answer is that yes, this looks like the green car body here looks very organic. It looks very almost like a tree or something, doesn't it? And the method I just showed you with this benzoa technique, where you're minimizing the aggregate strain energy of the whole system and choosing density so you minimize it. That's not the only way to figure out the most efficient load path. So the way you distribute these densities, I didn't mention this before, the way you distribute these densities, and you minimize the aggregate total strain energy, that becomes the most efficient load paths through your design volume, given those loading conditions. And just to double check that this is the packaging volume right here. This is the only place you can have structure. These are where the elements that would have the maximum density live after you've optimized for density for each of those 500 elements. So your 500D design space is this one, okay? This is a packaging volume for a car. I'll show you how we get there. This is the result. This is where the optimizer would place density in order to minimize the aggregate strain energy. This is then also the place where you get the highest stiffness per weight, the most efficient load pass resulting in the most efficient structure is that guy, subject to different boundary conditions. So the packaging volume can be a source of great friction within a company. This pretty much always is going to begin with something from the product design office, the people who do the styling of the car, right? They say, we want the car to look like this. Here's a CAD surface of the vehicle. And then you can think of filling all that in with finite elements. And then you got to start taking stuff out, right? Because you can't put a load path through the driver's head You need to have room for an engine. You need to have rooms for wheels. The wheels are the actual packaging volume needed for the wheels is complicated because the wheels are going up and down, and they're also turning in the front of the vehicle, right, and sometimes in the rear vehicle. And so they have these things called beehives, which are the full envelope of possible positions of the tire. And you have to subtract that for things like the battery, the suspension, the gas tank, the sunroof. Okay, this is what's left over. These are all the places that we determined you could put structure within this SUV here. These are all the places you could have structure. The loading conditions. So there's a lot of discussion about loading conditions. What loading conditions do you use for topology optimization? There are suspension inputs. That's pretty straightforward. There's sort of a global bending. We talked a little bit about this also. There's global torsion, global bending. There's front impact, rear impact, side impact. How do you, this is a source of great discussion. How do you simulate these things non-dynamically? It's easy to talk about bending and torsion non-dynamically, but when you talk about an impact load, that's a little bit harder to understand because it is obviously very dynamic. So these are the conditions that we happen to use at Chrysler. You're holding the body by the shock towers. Some cases you're twisting. Some cases you're applying a load in the middle of the front seats that would simulate a bending load. And then front impact, we just distributed load across the front bumper. For rear impact, we distributed load across the rear bumper. For side impact, we distributed load across the bottom of the B pillar. This is one way you can do this. There are better ways, which came later, but this is the way we did it back then. Now I think they sort of do this in time steps where to simulate impact, for example, you have some impact which results in some deformation, which results in the calculation of a new packaging volume. Then you redo that and keep crushing this thing down until you're as far down as you want to crush it. But the result looks like this. It's kind of a crazy organic shape. I mentioned before this method that we use, this method from Benzoa, where you calculate the aggregate strain energy. There are other ways to do this. One way that we developed at Mercedes is called the soft kill option. And the soft kill option, and I'm bringing this up only because it's kind of shows how this is kind of organic. The soft kill option was trying to mimic what trees do, right? So when trees experience a load, they start growing cells in the area of the highest stress. You see this?
Yeah, it's like palm trees.
Like palm trees, right. So you put a tree in the ground, you took it from one place, you put another. The tree has no idea where the wind's going to come from. With time, the tree learns what direction the wind comes from, or the kid who comes up and hits the tree every day, or the tire that hangs off the side of it, whatever. And it starts growing tree cells in that area where the stress is the highest. Really kind of neat, isn't it? So we at Mercedes developed this tool called the soft kill option that mimic that. So we put together a car body, and then we apply these different stresses like I've shown you here. And then we calculate out, we find an element analysis where's the stress the highest. And then we started adding more metal where the stress is highest and take it away from places where the stress was low. But you got to see the danger in this because there's all kinds of different loading conditions. And if you choose the wrong one, maybe the car's going to be great with rear impact, but front impact, you got a big problem. It doesn't protect anybody. You have to be very careful about how you choose loading conditions, right? How they represent real life the best. Okay, all right. So I think we got to stop for today. Next week we'll talk about the beam model, how you go from this crazy looking green thing or blue thing here, something that's more rational that you can then begin to put into real sheet metal stamped parts or aluminum extrusion or whatever you're going to use to make a real car body. So, and also one more thing. Next week we also will I'll give you a quick glimpse here. I'll show you what real cars use this. You can start to see this is a Toyota. There's a Honda Accord here. Anyway, we'll go through that next week. You'll see examples of where this top topology optimization has gone into real cars. And we'll talk about some other of the optimization. That's it. Thanks, guys. Any questions?
Thanks, Don.
Yeah,
Appreciate it.
I meant to mention that. I wish you guys on the phone could see this. This is a topology optimization result that we 3D printed at Chrysler, and then I stole it when I left. We had a series of these. This one's named Nimrod, but they all had different little names. And this is just a 3D print, we called it stereolithography back then, but just a 3D print of the topology optimization result for like a, what's called a D-segment sedan, so like your Toyota Camry or BMW, I don't know, 3 Series, Mercedes E-Series class. You can kind of see, you know, with this, with the different modes up here. You can look. Stop the recording. Guys, you're welcome to come down here next week and take a look at the 3D model. I can leave it here if you guys want to see it next week.
Sounds good.
Thanks, Don. I appreciate it.
You guys.
Thank you.
I noticed that some of the ones in the slideshow weren't like